Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com. And today we're going to be looking at derivatives of polynomials and exponential functions. If you like this video, feel free to click the like button. You can comment in the comment section. You can also share this video with your friends and classmates if you find it would be helpful to them. There are worksheets available in the comment section of the intro video, including this one. Let's take a look at the key ideas. So first off, given the opportunity, we should simplify before differentiating. And in general, we want to be applying differentiation rules in today's exercises. Some of the rules are given here to the left. Most of these are quite intuitive, and all of them can be derived by use of the limit definition of the derivative, which we looked at in a previous video. We also have here the notations for higher order derivatives. This one right here is the Leibniz notation. And we have the prime notation, which is also very prevalent in our work. Let's try this first problem. It reads, find f prime and f double prime for the following. In this exercise, we have a cubic polynomial function. To compute the derivative, we will differentiate term-wise. So we have f prime of x is equal to, recall we can pull out constants. So we'll pull the 2 out and apply the power rule, giving us 3x squared. For the next term, differentiating, we can pull the -9 into the front. And that's -9 times just 1. And for differentiation of the constant term, that is 0. We can simplify this, and we find that f prime is going to be 6x squared minus 9. Likewise, computing f double prime, we will pull the 6 out, and we get a 2x to the power 1. And the derivative of the -9 constant is 0. So our second derivative with respect to x of function f in part A here is going to be 12x. We use different color for the next function, and for part B, we'll use the color blue. So with this function, we may take a first step to maybe rewrite it in a slightly more suggestive form. Nothing to do with the e to the x, but we could rewrite the plus 1 over x cubed term as maybe plus x to the -3. And similarly, we'll write the -4th root of x cubed as minus x to the power 3/4. And the reason we do this is evident when we apply the power rule. It's preferable to have the terms in the form variable to some power. And by writing 1 over x cubed as x to the -3, and by writing the 4th root of x cubed term as we've done, it'll be easier to apply the power rule. So let's give it a shot. We have f prime of x. The derivative of e to the x is e to the x. The derivative of x to the -3, so let's just copy that plus symbol. We pull down the -3, and that's times x to the power -4. We reduce by 1. And likewise, we have a minus, and we'll pull down the 3/4. So that's 3/4 times x to the power. Well, it should be 1 less than 3/4. So taking away 1 from 3/4 is taking away 4/4 from 3/4. So we're down to -1/4. We could leave our answer like this or try to simplify it a little bit. So here, I propose to actually just leave it this way. And maybe when we compute f double prime of x, it'll be that much easier, still having powers rather than roots. So the derivative of e to the x again is still e to the x. And now we'll have what is a plus. We have -3 times -4 times x to the minus 5. And here this is minus 3/4 times a minus 1/4 times x2, taking away another 4/4 from already a minus 1/4 gives us minus 5/4. We may simplify this one. Here it is e to the x plus 12x to the power minus 5. And we have another plus term here. And the fraction is going to be 3/16. And we should just leave this term as x to the minus 5/4. There's no reason to get rid of the fractional exponent. And with that, we've completed problem 1. Let's try this problem number 2. It reads, find dy dx given that y is this quotient function. Well, one of the key ideas was to simplify at the onset of the problem where possible. I think we can do that here. So dividing the x squared into the two terms in the numerator gives x squared. And we have minus 16x to the negative 2. Next, we'll go ahead and write our dy dx. Notice we don't put an equal symbol with the expression to the left because the expression to the left is really just the y function simplified, or at least written in a different way. And the next quantity that we're writing is not equal to y, it's the derivative. So we'll apply now the rules of differentiation. We'll pull down 2, and this is times x to the power 1. And we have minus 16 multiplied by what is a negative 2 times x to one less value, which is going to be minus 3. Okay, we can go ahead and simplify this a little bit. So this dy dx is equal to 2x, and it looks like we have a plus. There's a 32 constant times x to the minus 3. Okay, next we'll go ahead and write dy dx evaluated at x is equal to 2 with dy dx. Let's just go ahead and make that look a little prettier. And the value we get is 8. And with that, we've solved yet another problem from this differentiation worksheet. Notice how we're using rules to perform the differentiation as opposed to using the limit definition, which we used in some previous videos. Let's try this next one. It reads, find ds dt, so that's the first order derivative of the s function, differentiation with respect to t, and then go ahead and compute the third order derivative. So we'll have to do 2 additional derivatives past the first derivative for the same function. So here, note that we have the first term being an exponential function, the second term being a power function with irrational power on the base t, and the third term is a constant. So first we'll do ds dt, and when we differentiate e to the t, differentiation with respect to t, we get e to the t. The derivative of t to the e is going to be computed using the power rule. So this is plus. We pull down the e, and that's times t to the power e minus 1. Finally, we have the derivative of the constant, which is 0. Note we are using different differentiation rules to differentiate those first 2 terms. We use a rule for exponentials for the exponential term and a rule for the power function, which is completely different, the power rule. Okay, this could be simplified by just dropping the 0 term. Let's just leave it for now. We'll go ahead and compute now what is d squared s dt squared. That is the Leibniz notation for a second order derivative of the s function, differentiation with respect to t. Well, once again, the derivative of e to the t is still e to the t. And for this power function, we'll have plus this e times e minus 1 times t to the power e minus 2. And finally, we can put what is the last of the derivatives needed. So this is d cubed s dt cubed. And we'll get e to the t plus, you guessed it, e times e minus 1 times e minus 2 times t to the e minus 3. We'll leave our answers in these multiplied out forms. You can detect the patterns that were used in the computations by keeping this multiplier in this factored form. We don't want to distribute the e in and multiply the e minus 1 by the e minus 2 unless your teacher tells you specifically to do so. We should leave our answers in such forms. In a way, it's even better for the instructor, the teacher, if they can see this multiplied out form, they can easily detect your method and whether it's correct. Let's try this next one. It reads, find the equation of the line tangent to the graph, y is equal to f of x, which is 2x squared, at the point x is 3. So this function, its graph is a parabola opening upwards. And at x is equal to 3, we can kind of visualize what the tangent line might look like. And you should be picturing a tangent line that is sloping quite a bit, but it's not vertical, and it has a positive slope. Now, whenever we're tasked with writing an equation for a tangent line to the graph of some function, if we know that the tangent line is non-vertical and the line's in the xy plane, I highly recommend writing a blueprint in the form of a point slope form equation for a line. This could be any non-vertical line in the xy plane, even if you're tasked with writing the equation for the tangent line in the slope intercept form, y is mx plus b. It may be a good idea to start here with the point slope form because it's usually easier to obtain the required quantities y1, m, x1, as opposed to getting little m and little b, the y-intercept. So in this particular example, we want the equation of the tangent line at the point where x is 3. So already one of the 3 values is known, the little x1, this is going to be 3. And inserting 3 into the function, we find y1. So it's 2 times 3 squared, which is 2 times 9, which is 18. So already we're 2/3 of the way done with getting the equation of the tangent line. The last thing to do is to get the little m value. And you'll recall that the derivative of a function, it returns the slope of the tangent line where you evaluate it. So that tells us that m should be f prime of 3. So in this case, we compute the derivative, which is going to be 2 times 2x to the power 1, and evaluate it at x is equal to 3. This gives us the value 12. So we can go ahead and insert 12 in and perhaps rewrite the equation of the tangent line as follows. So our equation of the tangent line is simply going to be y minus 18, and that's equal to our slope of 12 times x minus 3. There's no reason that we should try to solve for y here, though if your teacher does request that you write the equation in the slope-intercept form, by all means, just solve for y and don't make a blunder in the algebra along the way. We'll leave our answer in this form. And for the last problem in this worksheet on differentiation rules, we're kind of doing some applications right now in terms of tangent lines. This one reads, for what value of x, if any, does the graph of this function have a horizontal tangent line? So Let's go ahead and put in quotations here, horizontal tangent line. So what that means is essentially the graph is going horizontal instantaneously. So we want here a tangent line that has a slope of 0. Okay, so the slope of the graph should be 0, okay, when there's a horizontal tangent line. And we can go ahead and find where the slope is 0 by computing the derivative of the function. So we get, in this case, y prime, it's a function of x. It is going to be 1 minus e to the x. And now set this y prime of x equal to 0. And that gives us the little equation 1 minus e to the x is 0, which implies that 1 is equal to e to the x. So it looks like this equation only has one solution. By taking a ln of both sides or just converting to logarithmic form, we get that x is 0. So that is the only solution to the equation. Is there another value you can raise e to and wind up with 1? I think not. So just x is 0. So the goal was to find for what value of x, if any, does the graph have a horizontal tangent line. We can say there is a horizontal tangent line here. And with that, we have completed yet another calculus worksheet, this one being on differentiation rules, particularly the rule to differentiate an exponential function base e, as well as a polynomial. So I hope you enjoyed the video. If you did find it helpful, by all means, click on the like button. You can share it with your friends and your classmates if you think it would help them. Thanks and bye-bye.